In this talk, I'm going to discuss some local well-potency theory for the fifth-order KdV equations. So, first of all, let me just explain the relation between the KdV equation and fifth-order KdV equation. So, in fact, KdV equation is a third-order
다시 차례 팁을 올리세요.
The original KdV equation is a third-order equation with the linear terms, quadratic linear term with the derivative, and we can generalize the KdV equation by the changing each linear term to the higher degree power. But it is known that when p equal 1 or 2, when p is 1, it is a KdV, and then when p is 2, it is called the modified KdV equation. Then for both two equations, it is known that the equation is completely integrable in the sense that there is some sort of the symplectic geometric structure. It's called Lax pair. So because due to that structure, it is known that by such a structure that we can construct a hierarchy of the Hamiltonian equation of 2j plus 1. So when for the first one is a KdV equation, and the second one is fifth order, and the third one is seventh order or something. Okay? So for each equation is a Hamiltonian equations, and then associated Hamiltonian is just the conservation law is the next to the equations. Then, but by in that structure has the double Hamiltonian structure. So which means this Hamiltonian is a Hamiltonian of this flow for one Hamiltonian structure, and for the second Hamiltonian structure, that Hamiltonian is associated to the flow. So by such a Hamiltonian structure, one can show that the flow for each equation conserved every quantity on the right hand side, which means, for instance, for the KdV equation has infinitely many conservation laws, and fifth order equation does the same. So this complete integrability theory is very huge, and then mostly studied by the physicists or the geometer. But now the analyst job is just investigating such an equation in using the analytic tool, like so on the local initial value problem in Sobolev space. So the first motivation of the fifth order KdV equation is from the KdV hierarchy. So basically, in this motivation, that equation is not quite the physical because it is from just some abstract the formulations. But there is another motivation of the fifth order equation. So let me see the fifth order equation first. So fifth order KdV is a fifth order the linear terms, and it comes with the linear terms of quadratic linear terms with the three derivatives. So it may have two different terms, but the second one, when derivative they fall into the only one function, it is hardest. So when we work on the analysis, the analytic theory, if we can treat to U the three derivative of U, then the intermediate term is easily treated in the same way. So this is the some sort of the coefficient generalized the fifth order KdV equation. And in the same way, from the modified KdV, the hierarchy, that we can consider the cubic, the fifth order, the KdV equation. But in today's talk, I'm going to discuss only for the fifth order KdV equations. Okay. And the first motivation is from the KdV hierarchy, and then this is can be also understood as a higher order the model from the water wave problem in the range when the wavelength is pretty long and then with a small amplitude. Then if by the change of the scaling, then we can the full water wave equation can be approximated to the KdV equations. Or when the gravity effect and the surface tension effect are exactly matched, then the first order perturbation is gone. So now the second order perturbation is dominant. So in that case, the equation is exactly resemble to the equation we are looking for. And then there is two other model for of the fifth order KdV equation, but in the analysis theory, I'm going to just generalize each coefficient. Okay, so basically, the fifth order with quadratic with the 3 derivative. So from dispersive theory point of view, if we have a higher derivative, then usually the equation should be easier. So because the linear solution is in the frequency space, the linear solution has the stronger dispersion effect. So that means the phase space for this wave is equal to the first. So higher frequency data moving much faster than the KdV wave or the Schrödinger wave. So higher order the equation has a stronger dispersion effect, but the problem is nonlinear term. Nonlinear term has too much derivative, 3 derivative, two more than the KdV equation. So the reason why the fifth order KdV equation can be the issue is because it's the many derivatives of the nonlinear terms. Okay. Then let me just set the problem. Now I'm looking for the local solution for given initial data in some solar space HS. I'm going to looking for the solution for the short time in CTHS. Then first of all, the linear solution is formulated by Fourier transform, and then when you have F, inhomogeneous linear solution is given by the Duhamel formula. And then the solution we are looking for when F is replaced by the nonlinear term, then we are looking for the solution to satisfy these integral equations. Okay? And then because the operator ST is a unitary operator in L2 space, we can understand that equality is the equality in L2 function. Both are the L2 function. If they are same as L2, then we're going to accept it. It is a solution. Okay? So especially we call the solution for for initial data in HS, and then if the solution is in CTHS space, the continuous in time, and then superlap space in space, then we call this is a strong solution, as opposed to if the solution is L infinity in time or HS, then it is a weak solution. So, we are not going to consider distributional sense, but the strong solution in the superlap space. So usually we call an initial value problem is locally well posed if the 3 conditions is satisfied: on existence, uniqueness, and continuous dependence on initial data. Okay? The solution exists, and then it's unique, and solution map from the initial data to the solution in the topology from HS to CTHS is continuous. Then we call it is locally well posed. Okay? And for such the local well-posedness problem, in fact, there is a very two. I think we have only two methods, the general method to solve the problem. One is a contraction mapping problem, and the other is a compactness problem, compactness argument. So contraction mapping problem is like a fixed point argument, like like a Picard iteration. So we're gonna, for some given function space xt, x as is the regularity, and then t is the time. We're going to show that iteration map is a contraction. So by the contraction principle, by choosing the t to be small, then we can show. Once we can show that the map is a contraction, then we are done by the fixed point. But if the problem is solved by the contraction mapping problem, then we automatically know this inequality. So which means to the solution in the iteration space, which is embedded in the CTHS, is bounded by just initial data, difference of the initial data. Which means in this space, that inequality means the uniform continuous dependence of the initial data. Okay? So if the solution, if the problem is solved by contraction principle, then solution map is not just continuous, uniformly continuous, which means we have a stronger notion of the well-posedness, local well-posedness. And furthermore, if the nonlinear term is algebraic, like a polynomial, so in our case, our nonlinear term was just a quadratic, u sub x, then by the Duhamel formula, the integral form is a bilinear form. So we are looking for the solution to satisfying that equation. Then BUU is just integral form in the Duhamel formula. Like the third one, this one. This is BUU. Okay. Then if we find the linear estimate with respect to the iteration function space, and then bilinear estimate for that iteration space, then by using those two estimates, and then we can for the place of the u, we can plug in this formula in the place of u, and then in this place too, and then we keep replacing. We can write the linear solution as a power series of the linear solution. Then by using those two estimates for sufficiently small initials at the small linear solution, if the initial data is sufficiently small, then we can show that the power series is convergent. So that means the solution map is not only uniformly continuous, it is a real analytic. So the contraction mapping principle gives us a very strong notion of the well-posedness. Okay?
I missed something. What is XTS?
XTS is iteration space. So in fact, when we solve that problem, we are going to find some sort of iteration space which is embedded in this. So if we find the solution in the iteration space, that means they find the solution here.
Can you use your pointer, not finger?
Yeah. Okay. So, but in my problem, the fifth order KdV equation, the big difference between KdV equation and fifth order KdV equation is the notion of the well-posedness. So let me just quickly review what's happened in the KdV theory. Because when I first encountered the fifth order equation, I thought that the fifth order equation, KdV equation, is solved very similarly as KdV equation, but it turned out that there is a different story. So for the KdV equation, we have a very good local theory for very low the regularity, even for the negative regularity. Every local well-posedness theory, KdV or modified KdV or any generalized KdV equation is solved by the contraction mapping principle. So it means we have a good iteration function space, and then the solution maybe is a real analytic. But in the end, one of the previous result for the fifth order KdV equation is done 94 by the Fongse. The local well-potedness is done by when S is greater than or equal to 4. And then he used the energy method and then couldn't use the iteration method. And the other problem, the Koenig-Fongse-Vega, they find the local well-potedness theory for the decaying initial data. Now, I'm looking. Our problem is just a Sobolev space when initial data is in HS. But in their solution is when initial data has some sort of decaying power, then it can be solved by the iteration method. Okay? But without this assumption, it is impossible. Okay, so let me state the main theorem. The main theorem has a twofold. One is positive, one is negative. One is the positive result, well-potedness. So I'm going to present in the second half how we show the local well-potedness for some sort of low regularity, the initial data, and then so far I can show that. The local well-potedness for S is greater than 2. Okay. And then before then, I'm going to present the ill-potedness result first. So here the well-potedness means the standard, the meaning of the well-potedness, which means the existence and uniqueness and the continuous dependence in initial data. Just constant. But the ill-potedness result is a lack of uniform continuous of the initial data, which means the well-potedness and ill-potedness is not inconsistent, so they're consistent. Okay? Which means the solution map is continuous but not uniformly continuous. Okay? So then from previous observation, because once you have such an ill-potedness result, obviously we can see that the problem, initial value problem, it cannot be solved by the iteration method. Okay, so it should be solved by the compactness argument. So which means for given a smooth initial data, so we find the a priori bound for the solution, and then by taking the limit and using the priori bound, we can find the solution in some function space. Okay, so that's I'm going to present later. Okay, so lack of uniform continuity. So in other words, the solution map is not uniformly continuous for S is greater than 2. But S is great for all is not quite important because we need to use the local well-potedness theory to show the ill-potedness result. Ironically, so we can just claim this one. But if we have a better local well-potedness, then the regularity can be lower. Okay? So if the interpretate, then this can be we can find the two sequence of the solutions. Initially at time 0, they are getting closer, but at some positive time, for arbitrary small, the positive time, they keep a constant difference. Okay, so initially they are getting closer, but if the time is positive, then they have the constant distance. Okay, so once we find such a two sequence, then the solution map is not uniformly continuous. So the well-potedness, the theory is different from the KdV or the linear-Schrödinger equations. Okay. In the later argument, I'm going to make some note. I'm going to work on this simplified form. I just omit the intermediate term, but in the theory, it's not quite important. For simplicity, I'm going to just to look at the hardest in the linear terms. And by the scaling argument, we can also assume the initial data is to be small. So it is because the critical regularity for this problem is a negative the 3/2. So if the critical regularity is less than 0, then when we look for the solution is for S is greater than or equal to 0, then it is a subcritical problem. So for large initial data, now we want to find the short time solution. But by the scaling, we can transfer that problem into the small initial data for the time from 0 to 1. Okay? So we can assume that the initial data is to be small. But because this is a subcritical problem, it is equivalent to the large data, the problem. Okay. Okay. So first of all, let me see some sort of clue to occur the ill-posedness hint. First one is local smoothing estimate. So in the third order KdV equation, from the last talk, the local smoothing estimate recovered one derivative. But in the fifth order equation, because it has the stronger dispersion, so local smoothing estimate recovered two derivatives, so which is better than the KdV. Okay? So in general, if the equation has order the 2j plus 1, then the local smoothing estimate the recovers j's derivative, j derivatives. Okay. But the problem is because these recover only two derivatives, but remember that the linear term has a three derivative, more derivative. For the KdV equation, the local smooth recover one derivative, but we had only one derivative. It matched. Okay? So it was possible to solve by using the only local smoothing. But in that problem, because the linear term has too many derivatives, can be recovered by the dispersion effect, it is impossible to solve by solely using the local smoothing. So this is one clue, and then the second clue is some XSB, the linear estimate fails. Okay, so let me explain what is XSB space first. XSB space is, in other words, we can call it is a dispersive Sobolev space. Okay, so by definition, we have so if we don't have the second factor like a tau minus qc to plus I to the b. If we don't have such a factor, then this is a definition of the Sobolev space in the space time, with the s derivative. But but here we have one more factor. So one more factor it just play a role of the dispersion estimate. So okay. So in the elliptic equation, Laplacian u is f. Then if f is in L2, then by the Sobolev embedding, the u is in H2. So u has a two more derivative, two more regularity than f. Okay, so it is because the Fourier coefficient of the Laplacian is just qc squared. So okay. Then in the dispersive estimate, dispersive equation, so if we have 2d5, u is f, and then now we take the space-time Fourier transformation. So not just space. In the space-time Fourier transformation, tau is a temporal frequency, and then minus I qc to the 5 u, and then this is space-time Fourier transformation, tau qc f. Okay. So in the Fourier mode, the u, the f tilde has a one more this factor, then you tilde. Okay, so that means if f by this definition, if f is in the XSB space, by this definition, if f is in XSB minus 1 space, which means if f doesn't have one less this factor, then you should be in the XSB space. Okay, so the notion is pretty similar to the super-level embedding, but it is recently the discovered the use of such argument. So for the XSB space, we have such a linear estimate when the eta is just a time cutoff function. So because XSB, when you take the XSB space, we need to take the L2 norm in the space time. So for linear solution to be in the L2 in space time, we should cut off time. For instance, mass conservation law. By the mass conservation law, that without the cutoff time, if we take the L2 norm in space, because it is constant. If we take the L2 in the time again, then it should be infinity. But if we just look at only for the short time, then it can be in L2. Okay? So the inhomogeneous piece has the one less p factor. Okay? So this XSB, the space is a L2 based space in frequency space. So it has been very successful. It is originally introduced by Zhang Brogan in 1993. But such a type of the function space was extremely useful in the low regularity theory in the dispersive equation. And then there is a similar things in the wave equations, like or parabolic equation, like a parabolic super-level space or wave super-level space, something like that. Okay. So anyway, by using such a XSB function space, which is embedded in the CTHS space, we can successfully find the local well-potency theory once we have a good nonlinear estimate. So using this linear estimate combined with that nonlinear estimate, if it were true, then the story is end. But for the fifth order equation, because we have too many derivatives, that estimate is not true. And then the counter example of this nonlinear estimate is a low-high interaction. So when the function u has a pretty low frequency, and then v has a pretty high frequency, then because all the derivatives fall in the high frequency function, so u low frequency times high frequency could be some big number. And then the right-hand side, there is no derivative. Okay? So if it were the two derivative, then the estimate is true, but because it is has one more derivative, the estimate is not true. Okay? So this is just a close. That counterexample is just a counterexample for the XSB space. It doesn't say anything about the local well-potency, but it just give us some hint how to find the ill-potency counterexample. Okay? So from that observation, we can we notice that the low-high interaction was an enemy of the failure of the nonlinear estimate. So by using the low frequency data plus the very high frequency data, now lambda is frequency, using such an interaction, then we wanna construct the nonlinear ansatz. So if we apply like the p lambda, here p lambda is a little the Paley operator, which means just P lambda f is we take the Fourier transformation of f and then take the cutoff function between the P lambda of some function. It just means a frequency localized function to the lambda. Okay, so in more precise the definition. Sorry. Okay, so in the Fourier transformation, we're going to use just a simple cutoff function to define the P lambda. So this we just extracted the lambda frequency, the piece. Then the interesting piece is in the linear terms. The linear term has the low-high low interaction, low-high interaction, high-low interaction, and high-high interaction. But low-low interaction doesn't give us the piece of the lambda frequency. So we have only 3 terms. But among those 3 terms, the worst one is the low-high interaction. This makes the problem. The others are tractable. So in that answer, we want to observe that only that piece into the linear part. Okay? For the frequency localized solution, if we move only this term on the other side and then just the small terms in the are left in the right hand side. So basically, we are solving such a linear problem instead of the fifth order equation. Okay? So from this linear problem, we can correct its answer. So the answer as time goes, it has a low frequency piece and a high frequency piece, but high frequency piece take some sort of shift, but shift is done by the low frequency data. Okay, so this is not exact solution to our problem, but we can expect that this could be some approximate solution. Okay. So here, the correct example is as following. So when the phi lambda or the phi wide lambda it's just a cutoff function with the scaling. And then the reason why we choose here lambda to the 4 is because the speed of the propagation at the frequency lambda. And then we want to provide the support for a short time, for the time from 0 to 1, the greater than the speed of the propagation of the high frequency piece. Okay. Then initial data has also low frequency piece and then high frequency piece. Okay. But so here the capital lambda is just a constant to make the solution to be very small, and then the omega is just a sign +1 or -1. Okay. So we're gonna construct the 2 sequence of the solution. One is low frequency, and then high frequency data is overlapped. And then the other piece is low frequency is down, or high frequency data is overlapped. Okay. Then those 2 sequence at time 0, because the linear term, the high frequency piece are same. So, okay. So by choosing the omega +1 or -1, we're going to have the 2 sequence of lambda. One is plus, one is minus. When the low frequency data is upward, down. Then at time 0, the high frequency piece is the same. So difference of the 2 sequence is the difference of the low frequency piece. And at the HS norm, the low frequency piece is quite small. Okay? And from the previous answer, we can guess approximate solution is as like this. So here we have omega. If omega is positive 1 or negative 1, the phase of the two sequences is quite different. Okay, so that is the crucial thing of the approximate solution. So the goal is to show that we need to show at time 0, the two sequences is getting closer at HS norm. It is fine because the difference is only low frequency, and then at HS norm, this is small by its definition. But if time is positive, the approximate at least the approximate solution, their high frequency pieces are different. So difference of the two approximate solution is the difference of this with a +1 or -1. Okay, so they are quite different. They are greater than like some sort of t. Okay, for arbitrary small t. So if t is just a positive, then they have some constant distance, but they are going to 0. But this is just the that estimate is just to show that the approximate solution just take apart as time goes, at the positive time. So we need to use the local theory to show that the exact solution and the distance between exact solution and approximate solution are very small. Then by the triangle inequality, we can show that exact solution between of the two sequences also take apart. Okay? So to show that the exact solution is close to the approximate solution, one need to show the estimate. Which means if we just plug in the approximate solution to the equation, then if it were exact solution, it should be 0. But because it is approximate solution, it is not 0, but at HS norm, this is small. Okay? So by this argument, we can show that, okay, so using this, we can show that the approximate solution is close to the real solution, actual solution. As time goes, this is going to 0, and then this one, and the triangle inequality, they show, show that the exact solution at time t is take apart. Okay? So that shows the local ill-posedness. So in the sense that the lack of the uniform continuity of the problem. Okay, so once we show that the ill-posedness result, then now we need to use we know that we need to use the approximate method, also known as the compactness method, to show the local well-posedness. Then in the compactness method, finding a priority bound is the first step, and then the biggest step to show the local well-posedness, which means for given initial data is now in HS, but for the short time, if we assume that solution exists, then the CTHS, the norm of the solution is bounded by the initial data. Then by using such a priority bound, we can show and then by the same very similar argument of to find the priority bound, we can also show that the difference of the two solutions has also bounded by difference of the two initial data. Okay, by using such a two estimate, we can easily conclude the local well-posedness. But the crucial thing is to find the priority bound. So once we just present how to find the priority bound, then most experts on this method believe that it is locally well-posed. So at this time, I'm going to just speak about the priority bound. Okay? So this is number 3, that finding a priority bound for for S is greater than some number, is our goal. And then that goal will be obtained by the two P's. One is energy estimate, and then the other is estimate for the coefficient of energy estimate. So if we plug in this estimate into here, and then by assumption of the smallness of the initial data, then we can, and also by using the continuity argument, we can conclude the operator bound. Okay? So this is a two piece, and then, so let me explain the energy method first. So, so usually, such a problem, the usual the energy method work, but because in this problem, because we have many derivatives on the linear term, the usual energy method is not working. So let me show why. So in the energy method, for instance, when S is 3, see we take the 3 derivative on the equation and then integrate against the 3 derivative of u. Then the first term became this one, and then the second term is going to 0 by divergence theorem. Okay, because it has an odd number of derivative and 2u, then by the divergence theorem it is 0. And then from the linear term has a 3u, 1, 2, and then multiplying this, has a 9 derivative. We have 3 derivative, and then we're going to take the 3 more derivative, and then we have 3 derivative. So we have 3u and then 9 derivative. And then because the solution, the u, we're going to assume the u is just the smooth, well-decaying solution. We can freely use the integration by part. By the integration by part, all the terms falls in the two type. One is a 3 derivative equally distributed, and the other is the 4-4-1 derivative. So by the integration by part, the highest derivative, we can change the terms to the two factor of highest derivative has the same number of the derivative. Okay? So we have such a two terms, but if we don't have the last term is associated with the H4, so it comes with a 4 derivative. But in order to use the Groner inequality, if we don't have this, then for some sort of higher regularity, then higher regularity by using the super-level embedding, that we can find that the time derivative of this norm is bounded by itself, if itself with some sort of coefficient. But in this case, because it has a more derivative, that kind of argument is not working. So first of all, we need to handle the last one. To handle the last one, we modified. We add a correctional term to cancel this one. So first of all, we defined the third energy, E3. Then the first term is exactly the same as this one, but we have one more integral form. Then we take the time derivative and then use the inequality, use the equation. Then from the first one, we have this. We have those two terms. And then from the second piece, the integral, second integral, by using that equation, we have 4 types of the terms. And then one of them is the same as this one. Okay? So we can choose the constant A3 to cancel this term and this one. Okay? By such a choosing, we can show that the E3 is bounded by this term and then this one and then this one. But the lower two terms, it is easier because it has a lower number of derivatives, many use. So by using like the Holder inequality, that we can easily make it bound. Okay, so here the to overcome the difficulty of the distribution of the derivative, we use the correctional terms. Okay, by using such a correctional terms, we can find that energy form is bounded by H3, a piece of the energy form, but not exactly energy E3. But for the small initial data, it has a 2U, but it has a 3U. So if we assume that the U is small, then this term is comparatively much smaller than this one. Okay? So here we have to use a smallness assumption of the initial data. By using such an assumption, we can see that for the first term and the correctional energy, the third energy are equivalent. Okay? So once we find such a bound for the E3, then it's the same as we can find the bound of the H3 norms. Okay? So this is the first piece of the energy argument. So, so I just present that the theory for S is 3, so which is classical derivative. If S is a fractional derivative, we should use the commutator estimate. So because for the fractional derivative, the integration by part is impossible. So something analogous to the integration by part in the fractional derivative is commutator estimate. But because we need to move the three derivatives to other side, the Kato-Ponce commutator estimate is not working. So by using the similar idea, that we need to show that some new commutator estimate is associated with those terms. And then by the same argument, we can show the ES is, we can show the first piece, number 1 estimate. Okay? And then once you have just the first one, then if S is like a greater than 3¼ then by the Sobolev embedding, in one-dimensional case, Sobolev embedding, this is bounded by HS. So this CTHS is bounded by something about the HS. So we automatically find the a priori bound. So once by finding such an energy estimate, we can already improve the Ponce's earlier result for up to the S is greater than 3½ plus epsilon. But at this time, I didn't use anything about the dispersion effect. So for any function, this is bounded by like HS when S is greater than 3½ plus epsilon. But this is not any U. U is a good solution to a dispersive equation. So by using some sort of dispersive estimate, we're gonna show that this for some lower S. Okay. So now let me look at how to find the dispersion estimate to estimate the L so 3 derivative U at L infinity norm. So this is the Sobolev case. And then there is a 3 ingredient. One is a Kato local smoothing. When S is greater than the 5/2, then so we have a local smoothing estimate. You can observe that it has that local smoothing estimate recovers the 2 derivatives. Okay. And we need to also use the maximal estimate. So we're going to use the maximal estimate to complement of the local smoothing estimate because because if you look at the norm, like from the L infinity from 0t and on interval, but here we have a L2 norm on the same space. Okay, so by using the Holder estimator, we need both estimate. So the maximal estimate is also ingredient of the dispersion estimate. So it can be proved as like the Strick-Arch estimate. So second ingredient is maximal estimate, and the third ingredient is the Strick-Arch estimate. Strick-Arch estimate for the fifth order KdV equation or KdV equation comes with some sort of derivative, but not enough derivative. Okay. So LQ and RR should satisfy such a conditions, then we have a Strick-Arch estimate. Okay. Then when we estimate this by using the equation, by using the equation and and energy estimate, first of all, we have this, and then the second term, we use a Holder estimate to replace this one, and the one piece is for the Kato local smoothing, and then the other piece is for the maximal estimate. Okay? And then this is bounded by this bound is handled by the maximal estimate. This is by the Kato local smoothing. Then by using such a estimate, we can find we can conclude that this is bounded by HS norm of the initial data. And then this argument is work for the only S is greater than or equal to 3 and quarter. So it was just a little bit of the regularity. So here another ingredient of the theory is the refined Strick-Arch estimate. So intuitively, it is known that if we look at only the small time interval, then we can weaken the low and high frequency interaction. So that argument is already introduced into the other equation, like Benjamin equation, and originally by the Koch and Chebekov. And then they have shown that such an estimate. This is basically the Strick-Arch estimate. They look a little bit quite different, but when you show that estimate, for given you, we chop out into each frequency piece. And then for each frequency piece, we use the Strick-Arch estimate for the small time interval depend on the frequency. And then we combine every piece together. Then we're going to have such an estimate. Okay, so this is quite this is technical, but basically we can call this is some sort of a refined version of the Strick-Arch estimate. Okay. So if you look at the Strick-Arch estimate, you can observe that we have some sort of loss of derivative on the right-hand side. And then we have a gain of the derivative, which means some sort of derivative on the linear term is moved to the linear piece. So when you have too many derivative on the linear piece, then we can make a compromise to move by using the estimate to move this derivative to here. So by choosing alpha is 1, then we have such an estimate. So we have one less derivative. So because the linear term has one more derivative, then can be recovered by the local smoothing. But this is good news. It's just the linear term has one less derivative. So, and then this is true when S is greater than 5/2. So replacing the original Strick-Arch estimate by this one, we can improve the local well-positioning theory up to this point when S is greater than 5/2. Okay, so this is one story, and then I continue to work on that problem in quite a different setting to improve the regularity. That is the idea is pretty similar, but discard the energy estimate, but we use the XSB type structure. But the original XSB, the linear estimate is not true. But if we apply the XSB type structure into the tiny interval, small time interval depending on each frequency, then it's working. So it is because as we observed by the Koch-Cherenkov, by applying that, we can weaken some sort of the nonlinear derivative on the nonlinear term. Okay, so this is looking completely different. First of all, I'm going to define the function space. The solution U will be in the Fs for time t, and then this function space is embedded in CTHS. And the nonlinear term U sub xx will be in nonlinear space, and then the U is also in some sort of the energy estimate and energy function space. Okay, so going to define that later. And then it comes with the three estimate. One is linear, not exactly linear, but something corresponding to the linear estimate, and then bilinear estimate, which is nonlinear estimate. And then the other is energy estimate. Okay? So just plugging in the number 2 in the third place, this right-hand side is written by just Fs. U of Fs square, and then the U yes we're gonna number 3 to estimate this term. Then combining those 3 estimates, we can show that the UFS is bounded by itself. It's a higher power. Then by the smallness assumption and continuity argument, we can show by combining 3 estimate, we can show the a priori bound. Okay, so here the crucial thing is is the success of the bilinear estimate. It was possible because we used the XSB type structure in a small time interval. Okay, then now let me just show how we define. The definition is pretty technical. So first of all, we need to take the Pellet-Lilliard operator. So UK is a frequency piece when the frequency is comparable to 2 to the k. And then we decompose into the frequency piece. For each frequency piece, we use XSB space. This is a definition of the XS like a half space. And then we're going to define, so the function space xk and fk or nk is the function space only for the frequency localized function like a uk or nk. So we're going to use that function space only for the the function, the frequency localized to the k. Okay, so this is the XSB structure, and then we use the XSB structure for the tiny interval. So here, eta 0 is just a time cutoff function from 0 to 1. Okay, so time cutoff function, but we have a scaling factor. That means u times eta 0 of these things is supported on the time interval of size 2 to the negative 2 to the k. 2 to the negative 2k. Okay, so this is a very small time cutoff function. Okay? And under that, for that piece, we use the XSB structure, but we need to say for given time. So now from 0 to like a capital T, and then we are going to use the XSB structure only for this time, but we don't know. We don't know on which place we take such an estimate. So we have to take the supremum by the translation. Okay, for any. But the length of the time interval is 2 to the negative 2 to the k, 2k. Okay, and then in the same way for the nonlinear space, is also defined in the same way with some sort of negative power. So because nonlinear factor has one less of this term. Okay? So this is actually the same reason that we have. Okay. And then, so those function space is a function space for from negative t to t. Okay, so when they are same, then but the original norm is defined because by the Fourier transformation, it should be defined in space, in whole domain. Whole domain. Right? So this is a usual the modification to some fixed time, and then now we're going to combine those frequency pieces by using the regularity. And then by combining like as like defining the Sobolev norm that we're going to define. The last the function space for the solution and the function space for the nonlinear terms. Okay, and the energy definition of the energy space is as follows, because it is because in the definition of the function space KFK or NK, because we took the supremum. Okay, so to compensate that factor, that we have to need to use some sort of bigger space. Some sort of bigger space, bigger norm of the A. So by using such a definition, and then we can the linear estimate is just can be shown by its definition, and then bilinear estimate is shown by very similar way to show the nonlinear nonlinear estimate for the XSB space by chopping out every single piece into each frequency piece, and then considering all kind of interaction, low, high, and high, low interaction. And then we can show such a bilinear estimate in that way, and the energy estimate is also proved in a very similar way. So by showing this, then we can improve. So here the energy estimate is true for S is greater than 2. So by by this argument on XSB type structure and time chopping idea, then we can improve the local well-putness theory when S is greater than 2. Okay, so this is a story of some sort of low regularity problem that we are pushing down. So for given the initial data, some people some people are satisfactory when we have a local solution for smooth initial data, but this kind of problem is about the low regularity. We want to push it down the regularity to its critical regularity, but still much high. We just have a low regularity, the local problem when S is greater than 2, but the critical regularity is negative 3/2. So it's still far from the critical problem. Okay, thank you.
Are there any questions?